Over the last 100 years, advancements in science and technology have allowed us to learn so much about where we came from and how our planet has developed over time. With our discoveries of old fossils, we know that life on Earth has existed for at least 3.5 billion years. But with Earth itself believed to have formed over 4.5 billion years ago, we still have very limited knowledge on what caused life to form in the first place, and much of the evidence on how it may have developed has actually been destroyed by the very life that it created. Sadly, we do not have a time machine, but we can look for places in our solar system that emulate early Earth. That's where Saturn's largest moon, Titan, comes into the picture. Although it's about half the size of Earth, Titan has the characteristics that we think are very similar to Earth in its early days. Titan has a thick atmosphere at around 4.4 times denser than Earth's and is the only moon in our solar system to have any noticeable atmosphere at all. Titan also has large pools of liquid which follow a similar cycle to the rivers and seas we have here on Earth, but instead of water, Titan has seas of methane which evaporate into clouds, causing it to rain liquid methane. In terms of scientific information, Titan is a gold mine for scientists, but sadly it's extremely difficult to get to, and because it's entirely covered in clouds of methane, it's nearly impossible to study the surface from a distance. In 1997, a collaboration between NASA, the European Space Agency, and the Italian Space Agency launched the Cassini space probe on a 7-year journey to reach Saturn. The probe was designed to study the entire Saturn system, including its rings and natural satellites, but Cassini didn't make the 7-year journey on its own. Attached to the space probe was a smaller lander called Hawkins, which was hoping to become the first spacecraft to land on Titan. Several months after entering Saturn's orbit, Hawkins separated from Cassini and started its journey towards Titan, and began sending back vital details about Titan's environment, like the fluid properties of the atmosphere and the nature of the moon's surface. As it descended, Hawkins recorded accelerometer data which could be used to deduce properties like density of the fluid, as we knew the aerodynamic properties of the probe. It took temperature and pressure readings to teach us about the thermodynamic properties of the atmosphere, and after 2.5 hours of descending through the unknown, Hawkins successfully landed on the surface, making it the furthest spacecraft landing from Earth ever completed. Although it was only designed to survive for about 90 minutes on the surface, Hawkins successfully recorded and sent back 350 images, revealing a world eerily similar to ours, with sharp hills and valleys and rivers of methane cutting their way through the landscape. As our quest to learn more about the origins of life continues, NASA's new mission called Dragonfly will begin its journey to Titan in 2026, and the work of the Cassini and Hawkins mission will be vital to its success. Dragonfly is a mobile lander fitted with 8 large rotors that will be able to fly around the surface like a drone, an incredibly difficult engineering challenge, and the data gained from Hawkins will be insanely valuable when designing the drone. Everything from its sensor layout, battery capacity, energy source, and propeller design will be dictated by what we learned, and those are exactly the engineering challenges we are going to investigate today. Dragonfly will have many of the same scientific instruments as the Curiosity rover. It will have a skid-mounted drill to take soil samples and run it through a mass spectrometer to learn more about the soil composition. It will be capable of quickly analysing elemental compositions at landing sites using a neutron-activated gamma-ray spectrometer. This instrument typically needs cryo-cooling, but thanks to Titan's sub-zero temperatures, this instrument can be passively cooled. It will, however, need to generate its own neutrons rather than relying on cosmic rays to generate them, as the atmosphere blocks too much sunlight. When it lands, a seismometer will give us information about quakes and reveal the thickness and nature of Titan's icy crust, sitting above what is thought to be a liquid water ocean. We think this because Cassini witnessed the surface shifting in position by 30 kilometers in just 2 years, indicating that the crust is floating on top of some kind of liquid layer. We can also look forward to incredible photos of Titan's surface, just like the photos we are currently getting from Mars. Since the air is thicker on Titan and the gravity is 1/7 of Earth's, Dragonfly will be able to achieve more thrust on a planet that needs less lift, drastically reducing the energy needed for lift compared to Earth. Yet, finding that energy to fly on the surface of Titan is not easy. Due to Titan's distance from the Sun and its thick atmosphere, the sunlight on Titan's surface is around 100 times weaker than it is on Earth, making solar panels impractical. Thankfully, we have a lot of practice in a different type of energy source through missions like the Curiosity rover, which was powered by a radioisotope thermoelectric generator. RTGs work by converting the heat from the natural decay of a radioisotope into electricity. Now, this isn't traditional nuclear energy like I have mistakenly said in the past. The RTG does use radioactive materials to generate electricity, but not through nuclear fission. It uses a simple principle called the Seebeck effect to generate electricity. The Seebeck effect essentially allows us to generate an electric current through a heat differential, as charge carriers will move from hot to cold. So, if we have a heat source and a way of cooling, we can generate a sustained electric current. Thankfully, radioactive substances generate heat as they decay, but choosing a suitable radioactive material is our first challenge. With any spacecraft, a light, compact design is paramount, but we also need the material to have a long half-life to ensure a long-lived energy source. We also need it to primarily produce alpha waves, as this form of radiation is most easily converted to heat in a compact space. As a result of these requirements, plutonium-238, strontium-90, and curium-244 are the most commonly used fuels. Next, we need a material that is both a thermal insulator to maximize our temperature differential and an electric conductor to maximize our current. These two material properties are typically linked. Materials like copper are a good thermal and electrical conductor, and a material like iron is a poor thermal and electric conductor. Using these materials in conjunction can create a crude thermoelectric generator, but the efficiency is very low. If we can create a material with the best of both properties, then we can achieve a higher efficiency, leading to the use of materials like lead telluride and tags, which is an alloy of tellurilium, silver, germanium, and antimony. The thermal electric generator used for the Curiosity rover could generate 110 watts of electrical power, but we will lose some of that power generation capability during Dragonfly's 8-year journey to Titan, as we cannot turn a radioactive element on and off on demand to conserve energy. In fact, Dragonfly's cruise vehicle will need to be equipped with radiators to bleed that heat into space to prevent overheating, just as the Curiosity rover did. We will also lose energy to keeping the craft at operating temperature, as the surface of Titan can reach temperatures as low as -180 degrees Celsius, and to keep some vital systems and scientific experiments running, leaving us with about 75 watts to charge while on the ground in a best case scenario. All of our activities will occur during Titan's daylight hours, so we will be aiming to charge our batteries during Titan's nights, which last 192 hours, the same as its daylight hours. So it makes sense to make our battery charge fully in those 192 hours, giving us a 14 kilowatt hour battery. For comparison, a typical Tesla battery is about 75 kilowatt hours. With a specific energy of 100 watt hours per kilogram, that will make our battery 140 kilograms. In practice, a smaller battery will probably be used, and even a 30 kilogram 3 kilowatt hour battery would provide us up to 2 hours of flight time at 10 meters per second, providing a massive 72 kilometer range. Even more incredible when you consider the Curiosity rover has only driven 21 kilometers over the past 7 years on its time on Mars. Of course, Dragonfly won't fly its maximum range in one hop and will likely take shorter, safer hops between interesting points during Titan's day, and one of the most impressive things about this mission is how the spacecraft will navigate its way around the surface. Since Titan is so far from Earth, just sending basic information to and from Earth will be difficult. The energy requirements to transmit data rises dramatically as a result of the inverse square law. The Hawkins probe had the advantage of being able to relay information to the Cassini space probe, which had a larger antenna and higher power. Unfortunately for the Dragonfly mission, Cassini is no longer in orbit around Saturn after falling into Saturn's atmosphere in 2017. So, Dragonfly will need to dedicate both precious power and weight to a large, high-gain antenna in order to communicate with Earth's deep space network. On top of the additional energy and weight requirements, the average round-trip communication time is around 2.5 hours, making it impossible to fly the spacecraft in real time. Instead, Dragonfly will navigate using its own vision. Much like the self-flying drones we have here on Earth, Dragonfly will use its cameras along with onboard gyroscopes and accelerometers to travel from one point to another. Dragonfly will be trained to identify suitable landing sites that are flat and free from any obstacles like large rocks and rough terrain. Originally, Dragonfly was intended to fly with a single rotor, but since helicopters are mechanically complex in the way they vary the rotor's pitch to vary lift, the idea was never developed. But with the surge of multi-rotor drone technology over the last decade, the idea for a quadcopter became much more feasible. Dragonfly will feature a total of 8 rotors mounted in pairs in a quadcopter layout. Unlike a helicopter rotor, which is designed to spin at a constant rate, the speed of each rotor can be throttled electronically to vary the amount of lift generated. Although it's less efficient to have rotors in this over-under configuration compared to a regular quadcopter, it does provide additional lift while giving some redundancy, as the aircraft will be able to achieve stable flight even with the loss of one motor or rotor. Since Titan's atmosphere is made up of mostly nitrogen and is much colder than Earth's atmosphere, the viscosity is much lower. Along with the higher density, this means the rotors on Dragonfly will be operating in a fluid with a much higher Reynolds number than they would be if they were operating on Earth. Reynolds number is essentially a quantity that informs engineers whether laminar or turbulent flow will develop. It's a little confusing as the number is not constant for every situation and depends largely on the application, but in general it can be described by this equation for flow in a pipe, where inertial forces trying to keep the fluid flowing are the numerators and viscous forces trying to slow down the fluid are the denominator. Here, a higher density will increase the Reynolds number and thus increase the likelihood of turbulent flow, and a lower viscosity will also increase it. Exactly the scenario we are encountering on Titan. As a result, the propellers had to be designed differently to work as efficiently as possible on Titan. They are, in fact, much closer in design to wind turbine blades than normal propellers, with a large amount of twist in the aerofoil. These propellers are a meter in diameter, much smaller than any wind turbine blade here on Earth, but as a result of that higher Reynolds number, the same design principles are applicable. Wind turbines are also designed to be resistant to a buildup of surface dirt, which will be a valuable property on another planet, with maintenance crews billions of kilometers away. We also need to factor in the lower speed of sound on Titan, which is about 194 meters per second versus 340 meters per second here on Earth, so shockwave formation can occur much sooner at the tips of our propellers. This means we have to be mindful of tip speeds, which are determined by prop diameter and rotational speed. Even with these unique environmental factors, Dragonfly will have a mass of around 450 kilograms with a fantastic range and max speed, allowing Dragonfly to first land in the sand dunes of Titan's equatorial region before eventually making its way to Selk Crater, an impact crater thought to contain all the building blocks of life that we are familiar with here on Earth, and may just give us some clues about humans' ultimate question: how did we get here? You may have noticed that I mentioned the inverse square law, but did not fully explain it. This is a law that applies to a huge number of physical properties, and it simply states that the intensity of a point source of energy will decrease with the square of the distance away from it. This applies to gravity, electric fields, and radiation, like the Dragonfly trying to send radio waves back to Earth. To learn more about it, you could take this course in gravitational physics to learn how Newton deduced that the force of gravity obeys the inverse square law, and help you understand some of the terms I use in my videos. This is just one small chapter in a course on Brilliant, and you can choose from many other courses to test your brain and learn more about our universe. Or you could complete one of Brilliant's daily challenges. Each day, Brilliant presents you with interesting scientific and mathematical problems to test your brain. Each daily challenge provides you with the context and framework that you need to tackle it, so that you can learn the concepts by applying them. If you like the problem and want to learn more, there's a course quiz that explores the same concept in greater detail. If you are confused and need more guidance, there's a community of thousands of learners discussing the problems and writing solutions. Daily challenges are thought-provoking challenges that will lead you from curiosity to mastery one day at a time. If I've inspired you and you want to educate yourself, then go to brilliant.org/real engineering and sign up for free. And the first 500 people that go to that link will get 20% off the annual premium subscription, so you can get full access to all their courses as well as the entire daily challenges archive.